Okay, so we're going to shift gears. So the first week talked about probability theory, statistics. Got a little homework there for you to do on that. Again, part of that's just setting the groundwork for what we want to do. You have to be familiar with those concepts because part of what we're going to do is start using those ideas to analyze our data. Now, the other big thing we want to learn is some Fourier analysis, spectral representation of data, things like this. So I'm going to start off with a lecture on that today. And on Wednesday and Friday, we'll get our first sort of application of how to use some of the methods we talked about in first week, and also how we use the spectral Fourier transforms to analyze data. We'll do a radar problem, essentially, for a couple days. Okay? And that will be a nice illustration of how you can bring to bear all these tools together to actually say something meaningful about things. Okay? But we have to lay down the basics of this. So for some of you, you've working with Fourier transforms a lot. Some of you don't. So we'll just do a little review. Okay? So let's start off with this idea that Fourier had, which is the idea that I could take any function and that I could, in fact, represent that function as a series, in particular, a trigonometric series, okay, like this. Let's say for some interval between negative pi and pi. Okay, so this is the idea Fourier presented. He said, basically, I can do this. And this was sort of a startling assertion in many ways at the time, because it was just like, you know, people had known power series and so forth. But this is another version of a power series, which is trigonometric series. Power series typically expand about one point. Here, you're expanding on an interval. Okay? All right. So here's the other thing that is interesting about this. You would normally say, obviously, this is going to hold for periodic functions, because I've given you periodic functions to expand with. So they're periodic on 2 pi. But the interesting thing is, I can still represent functions f of x, for instance, that have things like discontinuities. Even though this function here, or this expansion, is everywhere differentiable and things like this, I can represent, in fact, discontinuous functions with this kind of thing here. Okay, so we'll talk a little bit about that as we go along. So the question that arises, first, one of them is concerning the convergence of that series. We won't talk too much about that. The other one is, how do you actually get out these a of n's and b of n's? What are the Fourier coefficients of this thing? Okay? So if you give me a generic function f of x, the question is, I need a recipe for getting an and bn out of this thing. Okay? So what I'm going to do is just take both sides and multiply by cosine mx. Okay? And I'm going to assume for a moment that this series is uniformly convergent. Okay? And what I'm going to do is just take both sides, multiply by cosine mx. So I have cosine mx plus this sum. I have a of n cosine nx cosine mx plus b of n sine nx cosine mx. All right, I can do that. Multiply by function. Next thing I'm going to do, I'm going to integrate both sides from negative pi to pi. Right? So here we go. Negative pi to pi dx. 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 Okay? Easy enough to do. And now, what do these integrals all evaluate to? Where there's some really nice orthogonality, what we call orthogonality properties about functions, which are the following. Here's something to note. If you do this integral on that 2 pi periodic domain, you can easily calculate this up, actually. It's always equal to 0 for all values of nm, which are integers. Okay? So in the language of Fourier or spectral methods, when you expand in the terms of a basis function, that's called an orthogonality property. Okay? So it's very much like you take a vector, and if I define a point in some three-dimensional space, how do I uniquely characterize some point here? Well, what you would typically do, you would give it your x, y, and z position. Three vectors would specify anything in three-dimensional space, and typically the way we think of x, y, z is being orthogonal coordinates. Okay? So you take this idea, but now you're expanding something in function space. All right? And so the sine nx and cosine mx are just like the x, y, and z coordinates, but now in some functional space. And it's infinite dimensional because n can be 1, 2, 3, 4, 5, whatever. But that is just telling you this is like the x direction, and that's the y direction. They're orthogonal to each other. All right? So that's what that means. You can also calculate the following. That cosine of nx times cosine of mx dx is equal to, well, if n and m are equal, then this becomes cosine squared. It's an even function which gives you some value. And if n and m are not equal integers, this thing is 0. This thing becomes pi. Okay? Again, orthogonality. Cosine of nx is orthogonal to cosine of mx. And cosine, if n is equal to m, then you get something like cosine nx squared, which is essentially the length of the vector, or the eigen, or the space that you're in. Okay? Gives you the length of the weighting of that functional, or the length of that functional. Then you also have the following: sine nx, sine m. Oh, that should be an x right there. Sorry. Dx is equal to, same thing, 0, pi, n is equal to m, and so when you look at sines, sines are also orthogonal for different n and m on that space specifically. Okay, you have to always specify that. But if you have sine squared, of course, it's a positive function. You integrate the area of the curve, it's pi. All right. With those properties in mind, you can come back now and actually evaluate the a of n and b of n. Okay? So we come back here. That's the little aside we have. We know how to do some integrals. And we bring them into here. And you don't know what this integral is. I give you an f of x. Presumably, you could put this in here and integrate it up. But regardless, you just leave that alone for a moment. You have an integral to do here. Here, look at this. You're summing up over all the n values this integral. Well, when n is not equal to m, this integral is always 0, except for when? Except for when n is equal to m. Then it becomes pi. But sine and cosine, this is always 0. So this integral is easy. This integral is pi. And you only take on one value when it's n is equal to m. So it's going to give you am pi out of that thing. Okay? And so by using that kind of logic, and also that will give you the a of m coefficient. If I were to have instead multiplied by sine mx and done the same thing, I would get the bn coefficients. At the end of the day, here's what you would get. A of n is equal to 1 over pi, negative pi to pi, f of x cosine nx dx, and b of n is equal to 1 over pi, negative pi, pi, f of x sine nx dx. There you go. Those are the Fourier coefficients. You just use your orthogonality property, you pull these things out. That's the basics of Fourier analysis in many ways. You just say, I want to represent a function, sum of cosines and sines. How do I do it? Well, you first just expand it out, write your solution out as this, or write out your function as this, and you say, okay, What are the coefficients? Well, there they are. You give me an f of x, I can calculate all the coefficients associated with that. So let me write those here, actually. So philosophically, we have to talk about what you've done, because this is actually the power of the Fourier transform, at least in terms of what we want to do with it, which is what you've done now. You said, I will place this function in x by a set of cosines and sines, where the n represents the frequency of that sine or cosine. Okay? And the a of n represents the weighting of that frequency. So for instance, you could say, how much cosine 2x do I have? Well, it's given you by a2. Okay? So you're going to take this function, and you're going to represent it what's called spectrally, which is you're going to take the data in the x domain, or you could have replaced x here by t, just had some function of time, and you're going to take everything that you have here and represent it as a set of sines and cosines. Okay? And these sines and cosines all have different frequencies. And the amount at each frequency that you have is the a of n's and the b of n's. Okay? So you take your data and you represent it as frequencies. That's the big idea of Fourier. Now, why is that important? Well, it makes a big difference when you start thinking about digital signal processing, in which you represent everything in terms of the spectrum or the frequency components. Okay? Radar, frequency components. Images, frequency components. Almost everything we want to do, and in fact what we're going to focus in on in the next 3 to 4 weeks, is all about putting things and understanding how frequency components behave. Okay? We're also going to do what's called time frequency analysis, which is we'll be somewhere halfway between frequency and time and doing some manipulations. All of it towards extracting out meaningful things. Okay? Everybody okay with that? All right, so most of you already know this, or at least have some idea of it. Some of you are fresh off of it, like if you took 581 last quarter, you're like, he's recycling it from last quarter. Yes, I love to recycle. We're in Seattle. This is what we do, right? Okay. I should have got a green pin for it even. Okay, so that is working with a finite domain. Negative pi to pi. A couple other things I wanted to say is that we could also expand the function in a more general way, which is the way we really want to think about it, in terms of the complex representation of sines and cosines. Okay? Where the C of n are the Fourier coefficients, and the C of n n pi over L are given by the following, this integral here. Okay? What we know about e to the I x is just cosine x plus I sine x. Okay, so that's the connection between sines and cosines. But this is kind of a little bit more general. Notice the other thing I've done here. Instead of being on the interval negative pi to pi, I've generalized it to be on the interval negative L to L. Okay? You can get from one to the other just by a simple rescaling of your variables. But this is kind of the more general formulas that we want to think about for the purposes here. Still finite domain. X is an interval negative L to L. And now we're going to talk about also what happens if I don't want to work on a finite domain, 0 to 2 pi, but I want to work on actually the infinite domain. X goes from negative infinity to infinity. In other words, take L to infinity here. Okay? And when you do that, you produce what's called the Fourier transform. The Fourier transform happens on the domain, the infinite domain. Okay, the first thing we should talk about, there's no such thing as an infinite domain. We're going to be doing computing, right? So it's really nice on pen and paper when you're working in infinite domain. Everybody's good with that. And then I say compute something. You can't do it on an infinite domain. You're always going to approximate an infinite domain by a finite-sized computational box. Okay? So just keep that in mind. However, the ideas are just straightforward from here, which is to say the Fourier transform is defined as the following. You'll notice that the sums that we have over here for the finite box become integrals, essentially. And here is Fourier transform pair. How to get into the frequency space and how to come back out of the frequency space. Here's how you go in. You give me a function, and I multiply by this kernel here. This kernel, e to the ikx, is cosines and sines, essentially, right? Where the k represents the wave number. So this k is the wave number. Related to the wavelength, related to the frequency components. But notice, in this infinite domain, I am assuming essentially, I'm going to integrate over all x values, and I get a continuous function of k. In other words, all frequencies are present. Okay, I have a continuum of frequencies. In the previous example, I had finite frequencies. N equals 1. N equals 2, n equals 3. I was looking for frequencies that made things fit in a box of length 2L. Okay? Here, I don't have that constraint of a box of 2L. I have an infinite domain, and so essentially I have a continuum of frequencies. Of course, when we go to compute something, we will never do a continuum. We'll do a finite number of frequencies, right? All right. So this takes us from a representation in the x domain to a representation in the frequency domain. K are the wave numbers. So once you do this, this is exactly what you want. So for instance, I give the example of a bird tweeting and tweeting. Birds tweeted long before we tweet. Okay, so it does that. And then what you see, like if you were to look at bird tweeting data, you see frequency versus strength of their tweet at different frequencies. Essentially what you're looking at is the Fourier transform of the data. What they actually do, right, is they create pressure waves. That's what would be like the f of x. We don't plot a pressure wave, essentially, when we look at, hey, I want to analyze how birds make sound. We don't look at the pressure wave so much as what we do is Fourier transform that, and we look at what are the frequencies that the bird is making noise at. This is the f of k. Okay? A couple things. If you take bird data, and this thing's making noise, right? You take a finite window of time, right? Let me sample it, Fourier transform it. So right away, you move away again from this negative infinity to infinity. This is an idealistic concept, mathematically relevant. However, you're always really going to be doing this. Okay? So just keep that in mind. Now, once you're in the frequency domain, to get back out, you take this representation, you multiply it by the kernel with positive I, integrate over all the k values, you get back your representation. Okay? So you can go in and out of the frequency space, and there's this nice connection between the two. Yes?
Does the finite domain have to be big enough, or just...
This is always a question you have to evaluate. And in fact, it's one of the major question about signal processing. Sampling times. I'm reading in data, and I want to take time windows of data to process my data. What's long enough? Is it a second? Is it 10 seconds? Is it 10 minutes? Depending upon what the frequency content you're trying to capture, right? You're going to have to take a window big enough to capture what you need to capture. Now, you don't know that ahead of time. It would be very specific to your problem, right? So if you're looking, for instance, for data, maybe you have some data that's collected over, suppose you work with rocks. You're an Earth and space science person, and you're collecting data. To you, 1,000,000 years is, that's like a second, because some people are working with 10 billion years, and you're just doing 1,000,000. That's like, fast. Okay? But if you're looking at atomic transitions, you're talking about microseconds as being your scale. Okay? So depending upon your scale, it's going to determine what you do here. All right. All right, so that's the definition of the Fourier transform. Some very nice properties about the Fourier transform is the relationship between the Fourier transform and its derivatives. And this also has an interesting probabilistic interpretation. So let me come in here and talk about what is the Fourier transform of the derivative. This is what very useful property, by the way, of Fourier transforms is to say, I have this function f of x. I want to take its derivative. Now I want to Fourier transform that. Well, the definition, by using these right here, is you just integrate f prime of x e to the I kx minus dx. Well, what I can do is I can do integration by parts here, which is take this thing, and you differentiate it, right? Take the f prime, you integrate it. Did everybody learn the u v variables? Is that like the standard? That's all you did all of second quarter of calculus, right? It was some of this. It was great fun, I'm sure. Okay. Everybody go with that? And if you just apply this rule, basically what you end up with, and by the way, you make one assumption that f and its derivatives go to 0 as x goes to plus or minus infinity. Okay. Then when you do that, what you find is that basically f prime is equal to ik f. Very nice. So Fourier transform of the derivative is just, all it does is picks out an ik. All right? You can generalize this result to, if I take the Fourier transform of the nth derivative, I get ik to the n f. Now here's kind of interesting. If I were to take this quantity here and integrate it over the k space, right? This is just some function of k. These are like moments, right? If there was some interpretation of this thing here of being some probabilistic distribution, then I'm multiplying by k to the n, and these become moments. So the first derivative just pops out a k here, and so you have this sort of first moment calculation that goes on. All right? So let's keep that in mind, because later we're going to be talking about data that has a bunch of noise in it. Okay? So that's a very nice part of the Fourier transform, is this relationship to the derivatives. Okay? This allows us to solve, for instance, differential equations. And that's not so much the topic of this course so much, but it will be, but it's something you should know about. Okay? And I'll do a little example of that, and then we'll continue on. Okay. So here's the example I want to give, solving a differential equation with the Fourier transform. Y double prime minus omega squared y is equal to minus some function f of x on the domain negative infinity to infinity. I can Fourier transform it. Fourier transform of two derivatives pops out an ik squared. I squared is negative 1. K squared is k squared. Good. See how fast I was with that calculation? Just did it right in my head. I didn't even do it right, work it out. Okay. That's what that becomes. Minus omega squared y hat is equal to minus. I've just taken this thing, turned it into algebra. Right? That's the whole point of the transform. You get rid of derivatives. because the transform has this very nice relationship between higher derivatives and the Fourier transform itself, you just turn this into algebra, which tells you that y hat is equal to f hat over k squared plus omega squared. So to solve this problem, you take the right-hand side for function f, you Fourier transform it, divide by k squared plus omega squared, inverse Fourier transform it. There's your solution of y. Okay? It's a very nice, elegant way to do this. In the end, it leaves your solution as an integral form if you wanted to solve it analytically, for instance. But, you know, doing the Fourier transform computationally is pretty trivial. And I want to talk about a little bit about the Fourier transform and how awesome it is. You guys ready for how awesome? FFT awesomeness. All right. Here's what's awesome. You ready? Are you ready? I don't think you're ready for this yet. Do you need more coffee? Because you got to get psyched. No? Okay, just chug it. No. All right. FFT awesomeness. First of all, we're not going to talk so much about this here in terms of actually solving problems. But everybody who TED 581 knows how awesome FFTs are because you solved the problem and it was a lot faster using the FFT. And here's why. 1, low operation count. Generically, you'd think that doing an operation like an FFT, you can actually calculate out, it should be something like, if you break it up in n points, it costs you n squared to make this transformation. But it turns out there's some very nice algorithm that's developed that drops you down to n log n. Log n grows very slowly. Okay? So you can take a very big number, log n it, and it's not that big. All right? So this almost is linear. It's about as fast as you could ever do something, right? So if you can beat n log n, I've always said this, you beat n log n on a consistent basis, your career's made. You're famous. They'll name the algorithm after you, like the Matt Williams fast algorithm. It'd be awesome. I'm going to apply the Williams algorithm. Then everybody, you know him right here. You get his signature later. He'll sign the book for you. You knew him when. All right, so that's n log n, super fast. That's why you call it fast Fourier transform. You don't get that f there for nothing. That f comes because you can do that. So like maybe if you write your algorithm that beats it, you could have SFFT, super fast, or whatever. You know, you have to find one way to up this. But there you go. Put super in front of it. Other things about it. Typically, it works on some interval, negative L to L. Okay. It also implies that you have periodic boundary conditions. Right? You're expanding everything sines and cosines on this domain. Remember, sines and cosines, you're going to have periodic boundaries. Okay? The key to lowering the operation count is you put 2 to the n points on your computational domain. The algorithm works as follows. It takes a problem of size n. This is what these guys, Cooley and Tukey, developed in the 1960s to make the algorithm n log n. It takes an algorithm of size n, cuts it in two problems of size n over 2. Then you can cut those down to 4 problems of size n over 4, 8 problems of size n over 8, all the way down to n problems of size 1 by 1. 1 by 1 is really easy to solve, right? But then you have to reconnect it back up to the n by n, to the n you have, okay? And that's what costs you log n, okay? But this is what they came up with. So the process of breaking the problem down works if you have 2 to the n points, right? You've got to keep breaking it down all the way to n 1 by 1s. So if you say, I'm going to solve this with 17 points, divide 17 by 2, what do you get? You can't do it, can you? I mean, you can, of course. You can't do it and get an integer, can you? See, this is a problem. So the idea is you pick 2 to the n points, works it fast. By the way, nowadays, it almost doesn't matter so much because they found ways to do what's called padding. And so if you're dumb enough to give it 17 points for your Fourier transform, it'll go, okay, this is clearly not a serious person. Let's just handle this problem on the side. And it will pad it and make it fast like almost n log n. Okay, it'll add points to this to make it basically size 2n, essentially, for you. Okay? It doesn't even send a little note to you saying, like, hey, dummy. I mean, did I just call you that? No, it doesn't even do that. Although maybe it should. That'd be pretty sweet, right? MATLAB sending you nasty notes to your Google account. See if it could get through the spam filter. All right. Accuracy. The accuracy is awesome. It's called spectrally accurate. What that means is a lot of schemes are like, you know, I discretize, it's order delta x squared accurate, or delta x to the fourth. It's a power law, right? So whatever, it's algebraic. But spectral means beyond all orders algebraic, essentially. That doesn't mean it's infinite. It's kind of like infinite order. It doesn't mean you don't make mistakes. It just means that you have very high accuracy, exponential type accuracy, beyond algebraic. I'll stop at that, saying about accuracy, because actually quantifying that accuracy is kind of a pain. All right. Final thing in these Fourier series ideas is that if you notice, we're working here everything on a domain of 0 to 2, you know, 2 pi periodic functions. Okay? However, you don't necessarily have to constrain yourself to that. Essentially what you do is you take some function f of x, I don't know, say it's something like that. And when you do this expansion, essentially what you're doing is you're doing a 2 pi periodic extension of this thing. So it's some function like this. It's periodic. That's it. Okay. However, there are other things to do. There may be constraints that you have that are specific to your problem, where I can look at a function on an interval 0 to pi, and I can do things like I will only expand in cosines. Now, if you only expand in cosines, cosine is an even function. So essentially, I make an even function out of this thing, and then that's what gets expanded, so forth and so on. Okay? I've removed the entire sine series. Okay? All right, so that's something. You can also do odd extensions. Jeez, that's the sine, sorry. That's the odd one right there. Thanks for catching it, Matt. You're just sitting there going, oh, he doesn't even tell me. That's the odd extension. Okay, anyway, that's odd. I did that on purpose. I just want to see if you're awake. That's odd, sines. Evens would be something more like this. Okay, and then I should have picked something easier to draw. Yeah, something like that. And that would be cosine expansion. And there's some reasons why you might want to use sines or cosines in doing expansions. Okay? So you're not necessarily constrained to just being 2 pi periodic domains. Okay? All right, some commands to know, which we're going to do next. In fact, let me turn on the projector, and we're gonna pull up this MATLAB here. Let me see. Did you hear anything? Yeah, I usually have to just look and, yeah, it's coming on. Okay. Here's some commands to know. MATLAB, FFTX. Takes a vector x and Fourier transforms it. That's all you got to do. Right? The inverse Fourier transform, IFFT. There's a discrete cosine transform. That's the cosine transform. DCT. Sine transform, SCT. Interestingly enough, these are packaged in, they're not part of the standard MATLAB distribution. Is it? Oh, yeah. Sorry. Thank you. There we go. Math coming through for me. Woo! All right, DST. Yeah. These are not packaged, by the way, in the regular. They're, I think, in part of the signal processing toolbox. Again, signal processing toolbox. It means that we're going to do basically Fourier domain type manipulations with data. Okay, so they package that there, but at least we get the FFT and IFFT for free. Okay, so we're going to talk a little bit about the algorithm. I'm going to show you what the algorithm does. So at least you're aware that when you're working with the FFT, there's some things that happen with the FFT that you've got to be aware of. All right. All right. There's a price for awesomeness. And we'll see some of it right now. What's that? Discrete cosine transform and discrete sine transform. Those are what DCT and DST are. Okay, so let me laptop. Oh, okay, maybe it's going to just show up, and there it is. Look at that. There's our MATLAB screen. Okay, so mostly what again, some of you are very familiar with this because you work with it all the time, but this is, again, just laying down some of the basics so we can move on from here. All right. So here we are. Clear all, close all. I'm going to basically define a domain, size about 20, and I'm going to decide on a number of Fourier modes. In other words, when I discretize this thing, it's not a continuum of frequencies. It is a finite number of them. 128. Okay? This are things like e to the I 0x, e to the I 1x. By the way, e to the minus I 1x, e to the 2 plus or minus 2nx, 3nx, 4nx, all the way to 64. That gives you 129 Fourier modes, essentially. Okay? So that's what that does. Then I can define my domain as a linear space that goes from this negative L over 2 to L over 2 in n plus 1 points. And what I'm interested in is actually the first 1 through n of them. Now this is important. You throw on the last point, what are the boundary conditions here? Periodic. So the last point is the same as the first. So there's a total of 129 points, essentially. But the last point, since it's the same as the first, you throw it away. You don't throw it away. You take it out of your calculation. If you have the first point, you know what the last point is. So essentially, you have 129 points. I'm interested in the first 128. These are the things I want to calculate. All right? So that's sort of, in some sense, implementing the periodic boundary conditions. You're already setting this thing up to handle the periodic boundary conditions. Okay. That's our domain we're going to work on. And so now what I can do is say, let's take a function, Gaussian, simple function. Let's just plot this for a minute. Plot xu. And when I do that, there, look at that Gaussian. Turns out the Fourier transform of a Gaussian is a Gaussian. So what we're going to do is Fourier transform this Gaussian and look at the Gaussian we get. Okay? Very simple idea. And here's how easy it is to do. We call it ut for the transform of u is equal to FFT of u. We're done. So in theory, I should be able to say, hey, let's plot just what ut, the Fourier transform, is. And run. Doesn't look like a Gaussian, really, does it, to you? I mean, if you look really hard and you get some stuff on the F, maybe. But generally, it's not going to look like a Gaussian to you. All right. I thought the F thing was kind of funny, but nobody really cracked up with that. No? Okay. All right. Here's the deal with the FFT. In order for it to be n log n, you remember I said the following. You take a problem size n, break it down 2 of n over 2, 4 of n over 4, all the way to n problems of size 1 by 1. And you bring it back up. What's the connection problem between the n problems of 1 by 1 back to the problem that you had originally? Well, it turns out to do the algebra and keep the n log n speed, you connect everything through what's called a butterfly filter, essentially. And what it does is it takes your data, shifts it, and multiplies every other component by -1. Okay, so what you're seeing here is the Gaussian shifted and every other component multiplied by -1. Now, the reason it doesn't undo this for you is because it takes time, computations. It wants to give you an algorithm that gives the FFT as fast as possible. So it's not going to do that kind of cleaning up for you. It gave you the FFT in time, n log n. What you have to be aware of is that's what it's giving you. So when you go to manipulate things in the frequency domain, you have to understand that in the frequency domain, things are shifted. Okay? Very important. All right, so some commands to undo the shifting. You know, when shift happens, you just got to take care of it. And there's the FFT shift command. Ready? Here we go. I can just do FFT shift. There it is. What that's going to do is undo the shift. So when you look at it now, there it is. We still have the multiplication by every other component by -1. I'll take care of it right now in immediate time by saying let's just plot the absolute value of the spectrum. And the Fourier transform of a Gaussian is a Gaussian. One thing we haven't done, though, is we've just left this x-axis to plot 1 to 128. This is how many points we have. The question is, this really is as a function of what? K, which is our wave numbers. So how do we construct the K values that go along this axis? Okay? Because that actually ultimately is going to be very important for us to understand and manipulate. So the K wave numbers are pretty easy to calculate, especially now that we understand that things get shifted. First, you need this factor, 2 pi over L. The fact is, the Fourier transform in MATLAB believes you are working on a 2 pi periodic domain. You want to work, but we're clearly here working on a domain of size 20. You can see that here. I've picked a size 20, and I don't want to work on a 2 pi periodic domain. However, when you use the FFT, it does believe you're working on a size 2 pi, so all you have to do is have a rescaling. And here is the rescaling, 2 pi over L. That rescales everything to 2 pi. Then finally, sorry. Okay. Now what I want to do is define the Fourier coefficients, and here they are. K over 2. Let me make sure, -1. Not K. Now this seems a little bit crazy, but these are essentially, remember I have things like cosine 1x, cosine 2x, cosine 3x, cosine 4x. That's what these are. That's what these integers are. I've rescaled it to 2 pi, from L to 2 pi. That takes care of that. And now these are the wave numbers. Cosine 0, cosine 1, cosine 2, cosine 3, and sine 0, sine 1, sine 3. Okay? But why did I shift them? I go from 0 to n over 2 minus 1, and then negative n over 2 to minus 1. Remember, because I'm doing this. Okay? In Ellensburg, where I went to high school, we do this. Because that's what you do at a rock concert. Right? Everybody good with that? No? Well, anyway, that's what you do. You guys got to, where's your black? You start wearing black with like Metallica shirts, and then you do that. Okay? If there's nothing else we should learn in this class, is maybe that. Because that's easy to learn. All right, and we'll talk about how do you move your head with that later. But for right now, there's the shift. And you have to count for that shifting. So those are the wave numbers we have to understand. And so when I go to the plot, I can now plot this axis as the FFT shift of K. And when I do that, there you go. Now what I have is essentially a physically meaningful values of the wave numbers on the bottom. Remember, you divide by 2 pi over L. L could be, for instance, I'm taking data over a microsecond. Maybe that's my window. That's 10 to minus 6 in seconds. Then when you rescale this, remember, this is 2 pi over L, over microseconds, right? So this is giving you an idea of these wave numbers being something like 10 to the 6. Okay? So that's where you get your physical unit values out of this thing. And the reason we also leave the k shifted around is because I want to maybe compute a derivative of this thing. If you want to compute a derivative of the function, all you got to do is multiply by ik, and then inverse Fourier transform. Okay? So when you do that, and you have to remember that your FFT that you took is switched around. So when I have this ut, if I want to calculate the derivative, all I got to do is say, okay, ut first derivative is equal to, just take ut, or I times k times ut. That's it. I just multiply by ik. Remember, k and ut are vectors. And then the first derivative, let's call it u1, is just inverse Fourier transform of ut1. So now what I could do, let's break this here, is I could plot, for instance, x versus u, which is the function, in red, and I can plot x versus the first derivative in green. And then when I do that, there they are, the function and its derivative. By the way, this is if you can get away with it, if your boundary conditions are such that you can use the FFT, this will be your most accurate calculation of a derivative, numerically, that you can do. Okay? And in fact, in the notes, I'm not going to do it here in class, but if you look in the notes, you'll see that what I do is I do a comparison of calculating the derivative using fast Fourier transform versus standard methods like finite differences. And you can see just how much more accurate these methods are, essentially. Okay? That's if you can get away with using periodic boundary conditions, right? So if you can't use those, I also give you an example of how bad using an FFT can be. I give you everything. All right, there you go. Good with that? All right. We'll leave that. Last couple comments. How about the lights back on up top? Okay. So that's Fourier transform in one dimension. The great thing about Fourier transforms and also MATLAB is Fourier transforms are very easily accessible. And for what we're going to do starting for your second homework, we're going to do some radar problems in 3D. Okay? If you want to do a Fourier transform in 2 dimensions or 3 dimensions, 2 dimensions, you just do FFT 2, where now this is a matrix of data. Very simple generalization. If you want to do 3 dimensions, you do FFT, actually, however many dimensions you want, something like this. And here you put in your dimensions. You want a 3-dimensional, you put in 3 there. And x now is a cube of data. Okay? So it's not a matrix, it's cube of data. And what this FFT in 3 dimensions does is Fourier transforms in the x direction, y direction, z direction. Produces for you the spectral content in 3 dimensions. Okay? All the shifting happens. You have to understand that you have to unshift. And you can also shift and unshift in higher dimensions, just like you do in lower dimensions. Okay? And so then it's as easy as this. This is giving us direct access to just saying, I have some stuff. I want to look at its frequency components. It's one command. It's really easy to work with. And then you can start manipulating that. And that's what we're going to talk about is essentially what digital signal processing does is you take this data, you apply filters for it, you clean things up, you try to remove noise. But you do all this in the frequency domain. So you put it over here, you do all your manipulations, you come back out with an improved representation or denoised representation or cleaned up representation of what you're getting in your signal. Okay, that's the entire purpose of it. And we're also going to be taking this, putting it over there, and looking at different time slices and asking, okay, I got all this noise. Is there anything real in there? Well, what if I look at different slices of time and ask about what's the covariance between different slices of time? Is there anything that from one time slice to the next actually is statistically related to the previous time step. And just save that. In some sense, if it's all this noise generating the system, you hope that that removes the noise, and then what you're left with is the signal over time. Okay? See? Now you don't even want to leave, right? Because you probably want to get the hell out. Okay, listen, have a great day. See you Wednesday. I'll be sending emails soon about homework, turning it in, how to do it. You're just going to write it up by hand, paper, and turn it in. We're probably not going to do score later this quarter. We won't do score later this quarter.